Hello, students, and welcome to the second to last official instructional video of this course. You've made it this far, and now we're going to do the final topic of hypothesis testing regarding a parameter. So we're going to talk about the language of hypothesis testing. Some of you might know that a hypothesis is really an educated guess or an expectation that you might have prior to doing some analysis. Based on your insight around a parameter. So again, the parameter is a population value, which in almost all instances, we never can know directly. So we try to find ways to at least make some claim or statement, of course, with the possibility of some error about the population parameter by using what we know about samples and statistics. So let's dive into this last topic. So there's a lot of vocabulary that comes with hypothesis testing. I'm going to read this out to you because these definitions are critical for this topic. So a hypothesis is a statement regarding a characteristic of one or more populations. So in this segment, we're only going to deal with one population at a time, but you can also run a hypothesis test that compares two populations. I will include that information and that knowledge in a separate folder for you, but it will be labeled optional. It's not going to be covered in this course. The winter semester is too fast to try to get into two populations. So here we're going to make a statement about one population and also one parameter. So hypothesis testing itself is a procedure based on sample evidence and what we know about probability, all that work with sampling distributions. We're going to use it to test the statements regarding the characteristic of one population. So the null hypothesis, when we talk about the word null, it's what we believe to be true originally. So it is going to be written as a statement that will be tested. And it's a statement of no change, no effect, or no difference, and assumed true prior to collecting evidence. So you're going to make this claim prior to actually running the results and conducting the hypothesis test. The alternative is a statement that we are trying to find evidence to support. So the null hypothesis is what's in existence now, what is believed. The alternative is what we are claiming and we are trying to find evidence to support. So the steps in hypothesis testing go as follows. First off, you make your statement regarding the nature of the population. So this is where you do the null hypothesis and the alternative hypotheses. And then you collect evidence, which is your sample data, to test the statement. So you're going to gather a sample of data, you're going to analyze it, and you're going to use that in step 3 to determine the plausibility of the statement. In other words, is there enough to support the alternative or not? So in hypothesis testing, there are only 3 possibilities. The null hypothesis is most commonly written as equal, regardless of the alternative being tested. And the reason for that is the null hypothesis is what is believed to be true in this moment. So the parameter equals that particular value, right? That's what we claimed that it is at the start. And we conduct our test to determine one of the alternatives. So the two-tailed test alternative is that the parameter is not that value, that it's either smaller or larger than that value, right? So that is the claim of not equal. The left-tailed test, if we look to the left, we believe that it is actually smaller than the claimed value. And if it's a right tail, we claim that it is actually bigger than that value. So those are the possible tests. So let's talk about the outcomes for a hypothesis test. There are some correct outcomes. So suppose we reject the null hypothesis when the alternative hypothesis is true. So we say what was originally believed is rejected because there's enough evidence to support that the alternative hypothesis is true. The other correct outcome is we do not reject the null hypothesis when the null hypothesis is true. So if it is correct, hopefully we do not reject it. The incorrect outcomes, in contrast, are that we reject the null hypothesis when in fact, it was true. So we're saying that it isn't when really it is. That's a type 1 error. And then we could also not reject the null hypothesis when the alternative hypothesis is true. So then we're keeping the null, even though there would be enough reason for the alternative hypothesis to be stated as true. And that's a type 2 error. Why are errors important? Well, let's look at this chart. So the 4 outcomes are summarized here. If we knew the reality, we wouldn't have to do hypothesis testing, but let's just suppose that we know the reality to see what the correct outcomes are. So the reality is the null is true. We don't reject it. That's a correct outcome. If H1 is in fact true in reality and we reject the null, then we're also correct, right? Because we've settled on the alternative. Now, suppose H0, which is the null hypothesis, is true and we reject it. Oops, that's a type 1 error. And if the alternative is true, but we do not reject the null, then we make a type 2 error. So it's also summarized here as to which one's a type 1 and type 2 error. Let's use an example that might make more sense, because also the way that we phrase reject or do not reject for our conclusion, there's a reason for that, right? Because we don't know the reality, so we can't affirm that one of the things is true. We can only choose to not reject or reject. So let's use the null hypothesis is innocent until proven guilty. So anyone in criminal justice, I guess this slide is for you. And the alternative is the defendant is guilty. So in a court of law, we assume the null hypothesis until there's enough evidence to convict, right? To decide that the alternative is in fact true. So let's look at some errors here. So if the defendant is actually innocent, which only the defendant really knows, and the defendant is found not guilty, that's correct. So an innocent person is found not guilty, so they get to go free. The other correct one is over here. The defendant is guilty and the defendant is found guilty. So that means a guilty person is convicted, right? They go and they have to pay for the crime. Now, a type 1 error, which is down here, is that the defendant is innocent, but they're found guilty. So that means an innocent person is convicted. This is not a good outcome. So that's a type 1 error. And the other error that could occur is that the defendant is guilty, but they're found not guilty, so a guilty person is set free. Now, in terms of hypothesis testing, the area that we try to minimize is the type 1 error. So the type 1 error, the reason why we try to minimize that is because it's usually viewed as the more problematic type of error, right? So having an innocent person in jail is considered to be a more problematic outcome than a guilty person being set free. So the level of significance alpha is the probability of making a type 1 error. So we're going to try to reduce alpha as much as possible, but we can't have it at 0 because that's not possible, right? So we're just going to pick an alpha that reduces this as much as possible. And also, in terms of this example, right, it's important to recognize that we never accept the null hypothesis, right? We can only reject or not reject it. So this is really important, right? Because we can't accept the null. We can't say that the defendant is innocent because we're not sure, right? We either had enough evidence to say that they're not found guilty or that they're found guilty. So this is very subtle, but very important. We will never accept the null hypothesis as true. We can only reject or not reject it. So that's how we're going to phrase all of our conclusions. So let's discuss how to set up a hypothesis test for the mean. Then we'll set it up for the proportion, just for practice. We'll talk about how it's calculated, but in the end, Excel will be the way that you can run it through a hypothesis testing calculator that I designed. That makes the work a lot more simplistic, but it's a very powerful tool. So it's good to know how it works in the background. So take a moment to try to set this up. And if you want, you could pause the video. So I'm going to launch into the discussion of it. So we're going to talk about the null hypothesis. So what's believed to be true They calculated the mean at 17,072. So that's the null hypothesis for the mean. A researcher has a different belief, right? So the researcher gives us an alternative hypothesis that's changed. What does it mean to change? It means not equal. So the researcher isn't sure if it went up or down, but they're pretty sure that's not the same. So this is the test that this researcher will set up. In terms of proportion, here's another practice example. If you want to pause the video here, now would be a good time. And in terms of this one, we see 19.6%. So when you see a percent, it sort of leads you to proportion. And this is the percent of children who are overweight. So the null hypothesis is the Centers for Disease Control and Prevention, the CDC, said that it is 19.6%. So our null hypothesis is 0.196. A school nurse looks at the students in her district and decide, I think it's actually higher here. So that's going to be the alternative, that the proportion is actually bigger. And that's it. That's how you set up a hypothesis test. You have the original belief and hypothesis form, and then you have your alternative that a researcher or you would claim differs and in which direction. This gets into the part of statistically significant. So when the observed results are unlikely, if the null hypothesis were true, then there's this result that is statistically significant and we can reject the null hypothesis. So next slides, we're going to discuss how do we determine something is unlikely, or as we used to say, unusual. If you remember from the probability lecture, we called unusual less than 0.05, but different circumstances require different alphas, right? Different type 1 error possibilities. In the medical field, you want a really small type 1 error. You don't want to harm anyone. So usually you see 99% is the level that we use. So it would be a 0.01 alpha. And if we deal with things that are less life-threatening, some of these can go down to 90%, which would be 0.1 for alpha. So it really depends on the importance of minimizing a type 1 error. And that sort of drives the hypothesis test as well. Also, it's different than practical significance, right? So even though small differences might be statistically significant, if the difference isn't large enough to cause concern, it might not be of importance. And that would be how much it would cost to change whatever system is in place. Now, there are different approaches to testing hypotheses. So what we can do is we can look at the sample statistic that we calculate and see how far away it is from the parameter that is in the null hypothesis. So we make a claim that we believe is true, right? So the null hypothesis states the parameter is this. So that sets our middle for our graph. And then we run a sample to see how far away the sample is from that mean, right? From the hypothesized mean. If it's quite far away, it's unlikely that we would have gotten that sample. So that puts question on the null hypothesis, which is why we can reject it. Sorry for the noise in the background. If the probability of getting a sample statistic as extreme or more extreme than the one obtained is small, then again, like I said, we reject the null hypothesis. And the way that we calculate this probability is a p-value. So the p-value is this probability. It's the probability that a sample will result in a statistic such as the one that we got if the null hypothesis is true. So we're looking at the area of the little tails. So when we're testing a hypothesis, these are the levels of significance that I have laid out. So the first two steps we've just done, we determine the null and alternative hypotheses. We select the level of significance based on how serious it is to make a type 1 error. Again, Educational studies usually hover around 90%, maybe 95%. Medical studies invariably are around 99%. Now, we also have to watch out for the requirements, right? In order for this to hold, we need that sampling distribution to hold. So again, we have to make sure it's normal. So there's some tests here. The sample values have to be a subset of a large enough population. And for the third requirement, either the population proportion has to have that relationship, which would make it approximately normal, or for the population mean, we need a sizable sample size. So we need a big N, which we defined as bigger than 30 right here, because we see that when we run the simulations, that's where it transitions to a normal distribution, no matter what the starting population looks like. Okay, so next steps for the population proportion for testing a hypothesis. This looks scary. This is where Excel comes in. So there is this thing called the test statistic that we just mentioned, and its location can help you determine whether or not it's realistic that that value occurs, right? So if this test statistic is far away from the measure of center, right, the null hypothesis, then we know we have something unusual happening, and that's when we can reject the null. We're going to determine the p-value again using Excel, and the smaller the p-value, the more likely you are to reject the null. That's a simple way to look at it. And in particular, your significance level determines how small p has to be, right? So the p-value has to be small enough where it's less than your significance level. So whatever the alpha is for that type 1 error that you want to keep small, in health it would be 0.01, then your p-value would have to be less than 0.01 to reject the null. And then you're going to state the conclusion in words. So you're going to use the context of the problem to talk about what this means in the realistic real-world context. Now, if we're doing a mean, we're going to use the t-statistic. So remember in the confidence interval discussion, we talked about the t-statistic. We need to use it because we've estimated not only the mean, but the standard deviation. If you look back here, we only have one estimation that we do, p naught, right, and p hat. So we only have that one. Here we have x bar and s that we're estimating. So that's the differences. We have two calculations here. Here we have one. So again, Excel does that for you. It calculates the p-value for you, and the same rule applies for the p-value. It has to be less than your significance level, and then you'll rephrase it in terms of the realistic context. Now, just to get a graphical idea of what's going on, I'm going to put one graph up here just to talk about briefly, and then we'll move into Excel to use the hypothesis testing tool in Excel. So suppose we had a two-tailed hypothesis test. So here in this middle region, we have, if you see the H naught here, that's how we say this. This is the null hypothesis. That's our center value. That's believed to be the proportion parameter or the mean, right? So the population parameter of the proportion or the population parameter of the mean gets placed in the center here. We do a calculation using what we know about sampling to create a plus or minus situation with the standard deviations. And that gives us this region. And these critical values are based on Z or T statistic. And then the rejection region, see this alpha over 2. The reason it's over 2 instead of just alpha is because there's two sides. It could either be here or here. If it was only upper or lower tail, it would just be alpha. So this would just be alpha for lower, or this would just be alpha for upper. So that would be the only difference. So if your p-value is a probability that's within this purple shaded area or pink shaded area, purple pink, then if your p-value is in here, you would reject. If your p-value falls in this not shaded in region, then you would fail to reject. Same for the other side. The sample statistic, same thing. If the sample statistic is in the shaded area, we would reject. If your sample statistic that you calculate is within this area, you would fail to reject. And that's hypothesis testing. So it looks really complicated. The calculations are probably a little scary, but the idea is is pretty simple once you look at this a few times. So take some time to look at this, and then I will see you in the video where we use Excel to work through some sample problems out of the book, just like we did for confidence intervals. And then you have all of the information you need to be successful to complete this course. I'll see you at the last video soon.